Here we go again. Um, Today we step into one of the more difficult topics in electromagnetism, that of electromagnetic induction. This lesson, this topic will be broken up into kind of three little chunks. And today we're just going to look at what's called Faraday's law of induction. So far, we have learned that it's really moving charges that produce magnetic fields. Right? When charges move, magically the universe puts a magnetic field around them. And we had a rule to tell us what direction that magnetic field is. You shove your thumb in the direction of either the current or the velocity of the charge, and then your fingers tell you the direction of the field. So that's how electric charges create magnetic fields. They move. And we had the same rule for wires, remember? And we had a formula to tell us how strong that field is based on your distance as well. We also learned that a electric current inside a magnetic field will experience a force. And so here we've got battery, positive current's going to flow out here, down here. When that switch closes, positive current will flow up, and it will go down along this little swing here, and it's going to pass through the magnetic field, this external magnetic field. What's going to happen as current flows through that green swing? Well, from this perspective, the current is going to sort of flow into the page, if you like, through this field. And so you should put your fingers upwards and then your thumb into the page, and then you will see that there is going to be a force outwards. So let's see if that's true. Press play. Yay. So yeah, we deflected that little wire. That's the Philby force that we've been practicing. Now, if you were to flip the current, which you would do by flipping that battery, the force is going to be in the opposite direction. And we could also flip it by changing the direction of the external magnetic field. That would achieve the same thing. Cool. Hopefully you get the idea. Now here's the big question though. So if we can produce magnetism from electricity, right? When electric charges move, a magnetic field gets created around it. That does raise a question. I hope it has raised a question. If we can make magnetism from electricity, I wonder, are you thinking what I'm thinking? Could we make electricity from magnetism? That would be cool. That would be way cooler because electricity is quite handy, for making an industrialized society with cool technology and stuff. If we could produce electricity from magnetism, that would be groundbreaking. It's cool to make magnets. It's even cooler to make electricity. Well, the first guy to really investigate that was Michael Faraday in 1831, and here's how he sought to see if it could be done. He had a large amount of current that he sent into a coil, and the coil was wrapped around a piece of iron. The iron would trap the magnetic field and direct it into a second coil which had nothing on it except our galvanometer, or like an ammeter, to detect did anything happen in the second coil. So you have this one coil that's powered and this one coil that's unpowered, and we're just hoping that by sending magnetism into that other coil, maybe electricity will pop out the other side. This is the original iron core ring that Faraday built. And I put a link on Connect to a cool Veritasium video on this. But apparently Michael Faraday had to actually insulate these wires himself, because you can't just have uninsulated wires, the current would just jump across and not spiral around. We need that coiling to get the magnetic field. Apparently it took him weeks to insulate all these things himself. So what happened was, closed the switch, and he actually did see a little deflection. But then while the current's running, he sees nothing. Just a little deflection. Then when he opens the switch, shut it down, he sees another little deflection of current. And then nothing. So sort of success, but unexpected. He just gets a little blip when he turns it on, but while it's running, nothing. Then when he turns it off, he sees another blip of current, but in the opposite direction. So what's happening magnetically is when he closes that switch, the magnetic field builds up in the second coil. And while it's building up, there is a current. Then when he switches it off, the magnetic field would get weaker. And while it's getting weaker, he sees another deflection. So the conclusion that he draws is that when the magnetic field is changing, that's when he was able to produce electric currents. Changing magnetic fields induce electric currents. Sort of similar, we saw that only moving electric charges produced magnetic fields, not stationary ones, or only changing magnetic fields will induce electric currents. And that sentence there is a little bit deceptive. More specifically, I should say that a changing magnetic field produces an electric field. Electric fields have the potential to get charges moving. You have to actually put a charge in the field for that to happen. So we sometimes call this electric potential or voltage. In this particular case, this induced one, when you change the magnetic field, we sometimes call it an EMF, which stands for electromotive force, which is a terrible name because it's not a force, it's a voltage, it's a difference in potential. So anyway, you induce a voltage by creating an electric field, and if that voltage is induced in a closed circuit, well, then it will produce a current. So in that sense, changing magnetic fields can induce currents. So to summarize what Faraday saw, when the current in the secondary coil, this one, the current in the secondary coil is zero when the current in the primary coil isn't changing. So when he had all this big, strong current running through there, nothing would happen. But when the current in the primary coil was either building up or slowing down while it was changing, that's when we saw current in the secondary coil. More specifically, the size of the current that you get in the second coil is directly proportional to the rate at which the magnetic field is changing. We've heard that rate term before many times in physics. So how quickly you change the magnetic field matters. The quicker you change the magnetic field, the more current you get. The direction of the current depends on whether the magnetic field through the second loop is increasing or decreasing. Now, both of these 2 points here, these second 2 points, each of them is going to require their own law. In this lecture, I'm just going to talk about the first one. In the next lecture, I'll talk about the second one. So we won't worry about the direction of the current today. We'll just talk about, okay, how big is these currents that you get? What does it depend on? So realizing that the magnitude of the induced current is proportional to the rate at which the magnetic field is changing meant that Faraday could build a way simpler way to generate currents. And this was it. It's literally just a coil, insulated wire wrapped around, spiraled around, and then you grab a fixed magnet piece of iron and you shove it in there, and as soon as you push it in, you are changing the magnetic field through that coil, and you'll see a current. When you pull it back out again, you're going to see a current. As long as you're changing it, you're going to see it. So you can basically generate electricity just by shoving that magnet in and out of a coil. Don't believe me? Check it out. Dude pushes the magnet and pulls it, and whenever he is moving it, that's when you see a current. Similar thing, this is a a coil of 600 turns and he's just put a LED across there, and every time he shoves that magnet in and out, you can see that there's a current because there's a little blip on the LED. So just a quick little simple proof that this does actually work. Changing the magnetic field through the coil induces a current. Now, to sort of get mathematical on this, we are going to need to define much more precisely this idea of the magnetic field through the coil. What do we mean by the magnetic field through the coil? Since it's when I change that, that's when I get current. So I need to mathematize this idea of magnetic field through the coil. Think of the magnetic field as rain coming down. So rain in your room. If you wanted to catch the maximum amount of rain in your coil, and imagine your coil is you making a circle with your arms. So she's making a coil, a loop, if you like. She's in the orientation where she's going to catch the maximum amount of rain. Think of these as magnetic field lines. She's going to collect the most of them. This guy, if you change your arms by 90 degrees, he has the same area, if you like, same size loop, but he's not going to catch any rain. None of the magnetic field will pass through. And that's kind of the analogy that we can use to explain this idea of magnetic field through the coil. The quantity is called magnetic flux, and the symbol is phi, and sometimes you'll see a little b next to it, but you can probably just write phi. Magnetic flux, the easiest way to think about it is probably is the total number of lines passing through the loop. So that means this one has zero flux. There's no lines passing through that coil. This one's going to have some, and this one would have the maximum amount. It's going to capture the most amount of magnetic flux. So magnetic flux depends on three things. The magnetic field, right? The more of those blue lines, obviously the more you're going to catch. Like the heavier the rain, if you like, the bigger the magnetic flux. But it also matters the angle. Sorry, the area of the coil, how it's oriented. This one has no area exposed to the magnetic field. This one has some area. This one has the maximum area. And the third one is sort of related to the area in many ways, the angle of the field relative to the coil. So it only really matters field passing through the loop. So if you want to think about it, that blue magnetic field line vector can be thought of as having two components, and only the red one is really passing through the area. The green one has nothing. It wouldn't pass through, so it doesn't contribute to flux. So those three things matter. Strength of the field, how wide your coil area is, and the angle between them. And you get this formula. Flux is equal to magnetic field multiplied by area multiplied by cos theta, where that is the angle between a normal to the plane of the coil, which is a weird concept, a normal to the plane of the coil and the magnetic field. That's theta. If they're at right angles, then it's just B times A, which quite often it is, to be honest. Now, the unit of magnetic flux is pretty darn cool. The Weber, single B, so I don't get to claim any fame relation here. But 1 Weber is 1 Tesla meter squared, because magnetic field is Teslas and area is in meters squared. It's a scalar quantity. It has no direction. It's just the amount of magnetic field passing through the coil. Quick little test that you're tracking with me. Which diagram here would have the largest magnetic flux? Well, these two have the biggest area. These loops have the biggest area. And this one over here has way more magnetic field passing through than this one. This one has 6 lines, this one has 3 lines. So this one has the biggest area of all 3, and it has the most lines. So obviously this one contains the largest magnetic flux. Bonus question, which diagram has the largest magnetic flux density? You're going to see both of those terms, magnetic flux density. Magnetic flux I just defined is like the Webers, the Tesla's meter squared, B times area. Magnetic flux density is the Webers per meter squared, which would be Tesla meter squared per meter squared, which would just be Teslas. So magnetic flux density is just another way of saying magnetic field strength, B. So they are sort of synonymous terms. One implies Webers per meter squared, magnetic field strength, just Teslas, but it's the same thing. Oh, so did I answer the question? Which one of these diagrams has the largest magnetic flux density? Oh, which one has the biggest field strength? Looking at those pictures, I think that the lines on this one and the lines on this one are kind of the same distance apart. So that being how we represent fields, I'd say they have about the same flux density. Another quick question. So I've got a ring hanging on a piece of string. If I swing it back and forth like a pendulum, would that involve a change in flux? If I spun it, would that involve a change of flux? If I boinged it up and down, would that involve a change of flux? Which of these does involve a change of flux? Pause the video, make a prediction. And hopefully you only predicted this one. Number 2 is the only one that changes the magnetic field through the loop. Because when it spins 90 degrees, it's going to have no field lines passing through it. As this one swings back and forth, it's kind of like you holding out your arms to catch the rain and walking sideways. It doesn't change anything. And this would be like trying to catch the rain while bending your knees up and down. That doesn't do anything either. Only the middle one changes the amount of rain, if you like, changes the field through the loop. So that gets us to here. So this is the summary of all of that. So what Faraday saw was the induced EMF, or the voltage, in a loop of wire is proportional to the rate of change of magnetic flux. So now you know what flux is. Now you know how we can change it. And the change per second, the rate of change, that's what gives you your voltage. The rate of change in magnetic flux. N here is the number of loops. So if you have one loop, you get so much voltage. If you have 2 loops, it's kind of like basically you're doubling the area with every loop. So there's this N here for number of loops. The minus sign, you don't need to worry about it for this lesson. It's just telling you about the direction of the voltage, and we'll pick that up in the next lesson. Let's do one quick question, and then you should practice all of this. So imagine I tie my wedding ring, 1.5 centimeter diameter, and I spin it so that it rotates 90 degrees from this point. I don't have a picture, but you can imagine. Right now I just see the skinny side. So from here to that orientation in 0.1 of a second. Calculate the magnitude of the induced EMF if the only magnetic field passing through the ring is the Earth's. Okay, so I'm just sitting here dangling my ring in the Earth's magnetic field, which points north, and I spin it. What am I going to see? How much voltage? Let's do the math. So there's Faraday's formula. Now for us, the only thing that changes is the area of the coil as I spin it, the area that's exposed to the magnetic field. The magnetic field just stays the same. So really the change in flux is really just B times the change in area. Change in area would be final, take initial. Now where it ends up, 90 degrees from here, it has no area, right? You're not catching any rain, if you like. Nothing passes through once. This is the maximum case right here. So it starts at the maximum, finishes at the minimum 0. So final, take initial, where that's the area of the circle. I don't really care about the negative here. So I'm just going to simplify this. Remember, I only care about the magnitude, so I don't care about the direction. So I'm just going to say, okay, well then it's b pi r squared on t. I know what b is, 55 millitesla, strength of the Earth's magnetic field, times pi, times radius, which is half of 1.5 centimeters, divided by 0.1 seconds. So how much voltage will there be in my wedding ring if I do this? Not very much, 0.0001 of a volt. Not surprising that me spinning my ring doesn't produce epic voltages. All right, this is a hard topic. You should probably actually read 6.2, and then you should have a go at the questions. Well, happy quarantine, boys and girls. Don't forget to hit like and subscribe. Wash your hands, blah, 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 blah. See ya.